Have you ever wondered why prime numbers, those indivisible giants of the number world, are distributed the way they are? These mathematical behemoths, prime numbers, are the building blocks of the numerical universe, holding a unique place in the realm of mathematics. They are the atoms of arithmetic, indivisible and standalone. Every number you can think of is either a prime itself or a unique product of primes. The concept of prime numbers is not new. It dates back to ancient mathematicians who recognized their significance. They are like the DNA of numbers, and understanding them is key to unraveling the complex genetic code of mathematics. Their unique properties have fascinated and perplexed mathematicians for millennia. For instance, they appear to be randomly distributed along the number line, yet they also exhibit a strange orderliness. This dual nature, this dance between chaos and order, is what makes them so captivating. But the real intrigue lies in the fact that prime numbers are not just a curiosity of mathematical theory. They have practical applications too. They form the backbone of modern cryptography, keeping our digital world secure. So, how do we predict where these prime numbers will land on the number line? How can we understand their mysterious distribution? Enter the Riemann Hypothesis, a conjecture that has been teasing and testing the minds of mathematicians for over a century. Proposed by the German mathematician Bernhard Riemann in the mid-19th century, this hypothesis provides a potential roadmap to the distribution of prime numbers. It doesn't solve the mystery outright, but it gives us a tantalizing glimpse into the pattern underlying the apparent randomness of primes. The Riemann hypothesis, while steeped in complex analysis and number theory, can be distilled into a simple question. Can we predict the distribution of prime numbers? If the answer is yes, it could revolutionize our understanding of these numerical giants. To unlock the secrets of prime numbers, we turn to a 19th century riddle, the Riemann hypothesis. So, what exactly is the Riemann hypothesis? Well, it's a tantalizing conjecture in mathematics, named after the German mathematician Bernhard Riemann, who proposed it in the mid-19th century. At the heart of the Riemann hypothesis is a fascinating function known as the Riemann zeta function, denoted by Zs. Here, S is a complex variable, allowing it to take on both real and imaginary values. The zeta function is a fundamental tool in number theory, a branch of mathematics concerned with properties and relationships of numbers, especially the integers. The Riemann hypothesis makes a bold claim about the zeta function. It states that all non-trivial zeros of this function, the complex numbers where the zeta function equals 0, lie on a specific line in the complex plane. This is what we call the critical line. To unpack that a bit, imagine the complex plane as a vast two-dimensional sea. The real part of a complex number is its horizontal position in this sea, while the imaginary part is the vertical position. The critical line is like a lighthouse beam, sweeping across the middle of the sea, where the real part of S is equal to 1/2. The Riemann hypothesis suggests that if the zeta function equals 0 for a complex number, that number is somewhere on this beam. In other words, it's on the critical line. It's like a treasure map, guiding us to the mysterious zeros of the zeta function. But here's the catch. While we've found many zeros on this critical line, we haven't been able to prove that all of them lie there. That's what makes the Riemann hypothesis one of the most intriguing unsolved problems in mathematics. In essence, the Riemann hypothesis tells us where to find these elusive zeros in the complex plane. It's a mathematical mystery that has captivated minds for over a century and continues to inspire exploration into the deepest corners of number theory. You might be wondering, why does this hypothesis still remain unproven? Well, it's not for lack of trying. The Riemann hypothesis has been a mathematical enigma for over 160 years, and it has withstood the scrutiny of some of the greatest minds in the field. The challenges that come with proving the Riemann hypothesis are many. For one, it involves complex analysis, a branch of mathematics that deals with complex numbers and their functions. This requires a deep understanding of both real and imaginary numbers, and the ways they interact. Moreover, the hypothesis itself is intricately linked with the distribution of prime numbers, which has been a source of fascination and mystery for mathematicians for centuries. This means that any proof of the Riemann hypothesis would also have to deal with the unpredictable nature of primes. Despite these challenges, there is a significant amount of computational evidence supporting the Riemann hypothesis. In fact, the first few trillion non-trivial zeros of the zeta function have been found to lie on the critical line, just as Riemann hypothesized. But while this evidence is compelling, it is not a definitive proof. And that's what mathematicians are after: a rigorous, watertight proof that leaves no room for doubt. This is the gold standard in mathematics, and anything less is simply not enough. That's why, despite the overwhelming computational evidence, the Riemann hypothesis remains unproven. The Riemann hypothesis has been recognized as one of the most important unsolved problems in mathematics. So much so that it's one of the 7 Millennium Prize problems, for which the Clay Mathematics Institute has offered a $1 million prize for a correct proof. This underlines the significance of the problem and the importance of finding a definitive proof. It's a challenge that continues to captivate mathematicians all over the world, and a riddle that is yet to be solved. Despite our best efforts, a definitive proof of the Riemann hypothesis remains as elusive as ever. What does the Riemann hypothesis mean for us, and why should we care? This question might have crossed your mind. It's not just about complex mathematical equations or a $1 million prize. It's about understanding the very nature of numbers, the building blocks of our world. The Riemann hypothesis has profound implications for the distribution of prime numbers. These numbers have always held a certain mystique for mathematicians, being indivisible save for one in themselves. The hypothesis suggests a deep, intricate connection between the distribution of these prime numbers and the properties of the Riemann zeta function. If proven true, we could closely approximate the distribution of prime numbers using the zeros of the zeta function. Beyond the realm of pure mathematics, the implications of the Riemann hypothesis stretch into practical fields as well. Take cryptography, for instance. It's the science of encoding and decoding information, the invisible armor that protects our digital lives. Prime numbers play a critical role in cryptography, and a better understanding of their distribution could lead to advancements in this field. In number theory, the Riemann hypothesis holds significant importance too. This branch of mathematics deals with the properties and relationships of numbers, especially integers. A proof of the Riemann hypothesis could lead to breakthroughs in number theory, potentially unlocking new mathematical methods and concepts. But perhaps the most profound implication of the Riemann hypothesis is the potential paradigm shift in our understanding of mathematics itself. A proof would be a testament to the power of human curiosity and intellect, proving once again that we can unravel the universe's deepest mysteries. So why should we care? Because the Riemann hypothesis isn't just a mathematical puzzle. It's a quest for understanding, a journey into the heart of numbers. It's a testament to our ceaseless pursuit of knowledge, pushing us to ask, explore, and understand. A proof of the Riemann hypothesis would be a landmark achievement, fundamentally reshaping our understanding of prime numbers. And that indeed is something worth caring about. So where do we go from here? The Riemann hypothesis, a conundrum that has puzzled mathematicians for over a century and a half, continues to stand tall, unyielding in its complexity. Yet hope is not lost. The mathematical community remains fervently dedicated to unraveling this enigma, their fascination with the problem as enduring as the hypothesis itself. In our modern era, developments in computational power have allowed mathematicians to verify the Riemann hypothesis for the first few trillion non-trivial zeros of the zeta function. These findings, while not constituting a proof, do lend substantial weight to the validity of the hypothesis. They also serve as a testament to the relentless pursuit of understanding that fuels the mathematical community. Yet, the quest for a proof extends beyond mere computation. It requires a deep dive into the abstract world of complex analysis and number theory. It demands the exploration of new mathematical terrains, the development of innovative techniques, and the courageous reimagining of established mathematical truths. Indeed, the allure of the Riemann hypothesis lies not just in its potential resolution, but also in the journey towards that resolution. The quest to prove the hypothesis has already led to significant advancements in mathematics, and every attempt, successful or not, contributes to the collective understanding of the mathematical universe. Moreover, the Riemann hypothesis holds a unique position in the realm of mathematics. Its solution would not only illuminate the intricate dance of prime numbers, but also unlock new pathways in various other fields, including cryptography and quantum physics. It is this potential for far-reaching impact that continues to fuel the fascination with this enduring problem. As we stand on the precipice of mathematical discovery, the path forward remains shrouded in mystery. Yet, the journey is filled with promise and potential. The Riemann hypothesis continues to beckon mathematicians, challenging them to push the boundaries of understanding, to question, to explore, and to discover. As we delve deeper into the mysteries of mathematics, the quest to solve the Riemann hypothesis continues to captivate the minds of mathematicians around the world.